now, today what we're going to do is we're going to talk about some properties of logs, what a log is, right? And then we're going to prove some of those properties of logs, the ones that we've used over and over again, and maybe not known why they were true. So let's start by just remembering them. Here's an old one. The log of a times b is equal to the log of a plus the log of b. We'll call that rule number one. Second rule, the log of a divided by b is the log of a minus the log of b. And then this one here, the log of a to the c power is c times the log of a. Now, these are the three most common rules for logs you'll see in most textbooks. I've looked in some textbooks and seen a fourth rule. The rule was like this. It said that the log of 1 over a is equal to negative log of a. And this will be our first question today, and that is, do you think this really should be a new rule? Do we need to write this down and say, oh, wow, this rule is definitely different from the others. It's something new. Or is it really just a direct consequence of one of the other rules that we already have? So the answer is no, we really don't need this to be a new rule. If we just take a look at the third rule here, we could think of this log of 1 over a as the log of a to the negative 1 power. We know that if you have something to the negative 1 power, it means 1 over that quantity, right? But according to rule number 3, that's just negative 1 times the log of a, or negative log of a. So rule 4 is really a direct consequence of rule 3. And I'm not sure why some texts will actually make a big deal out of this as a new rule. But you really don't need to. And that's actually like a good thing to know mathematically, to think about, right? It's like, do you have a set of rules? Do they sort of create everything you need? Or are there other rules that would be nice to have that are really genuinely different? So let's talk about that. As I've been reminded here, or been told to look at. If you look at rule 2, there's a way to use that rule to get rule 4. So let's think about our expression. We have the log of 1 over a. Well, that's the same thing as the log of 1 minus the log of a. Now, this actually is a good time to segue into the next part of the conversation. What does log of 1 mean? It's actually asking us a question. So before I go to that, I want to go back, and we'll come back to this in a minute. Let me start with a simpler example, something I think is simpler. You'll have to decide for yourself. Suppose I ask this question, log base 2 of 8. All right? So I'm going to say this. When you see this expression, what I'd like you to do is think of the following question. This is really saying, what power do we put on 2 to get 8? What power do we put on 2 to get 8? You kind of have to appreciate how compactly we can write this question, right? This is another little meta lesson about mathematics. A lot of mathematical symbols have a lot of meaning to them, but they don't take up much space on the page. So you should like that. This is this thing I've circled in blue is a way of saying what power do we put on 2 to get 8? And we happen to know the answer to that. The answer is 3. That's the answer to that problem. Okay. Let's do another one. Suppose I had said to you the log of 25 of 5. Now let me be clear about how you say this. This number here on the bottom, this 25, is called the base. So sometimes you might read this as log base 25 of 5. That's how you would say it to someone if you're going to read that off the page. Okay. So what I'd like you to do is just think, what question is this really asking? So this is saying, what power do we put on 25 to get 5? The answer to that is 1/2. Okay. And let's just go to a new one. Suppose I write this, log 100. Okay, so here we are, I'm writing log 100. You'll notice the base is missing. You may have learned in the past, but you should remember now, that when you don't see a base, you assume it to be 10. If you do that, you'll be fine. So log base 10 of 100 is really saying, what power do we put on 10 to get 100? And the answer to that is 2. Okay? Now, the 3 examples I've done so far had nice integer, well, not integer answers, but they had answers that you could sort of figure out. The only one that was tough maybe is just one in the middle. But if you think about it, 25 to the 1/2 power is really the same thing as the square root of 25, which is 5. So maybe it's not so bad. This one we just did was not bad at all, really. We know 10 squared is 100. Just know that you can ask other questions. I could say to you, hey, what's the log of 117? And you might not know the answer right away. You might not be able to look at it and say, oh, the answer is 2 point something, something, something. But you know what it's asking. This is saying, what power do I put on 10 to get 117? So we can write these things down, and we know what they mean. We might not always know what the answer is. Okay, so having said all that, let's go back to this second way to show that rule number 4 is really not necessary as a new rule. This is using rule number 2. So here's the expression we were at. We're right here. We have the log of 1. What question is that really asking? So the answer to that is 0. Well, now you have the log of 1 over a equals 0 minus log a, or negative log a. Oh, wow, sure enough, that's another way to do it. Right? Now we've shown that rule 4 is a direct consequence of both rule 3 and rule 2. All right, nice to know. Next. You're correct. All right, so here are the next things that I want to start to look about. First off, if you look at any of these expressions that we just sort of figured out, what we say is all of these things were written in log form. Okay? Because you had logs in the expression. Every one of them can be rewritten in something called exponential form. So here's what I mean. Let's take this first one. Log base 25 of 5 is 1/2. That's true because 25 to the 1/2 power equals 5. So the thing on the left over here, this is called the log form of the equation. And the thing on the right is called the exponential form of the equation. Okay? If you ever have trouble figuring out what the exponential form is, just think about how you answered the question. That's all you have to do. All right, so let's look at that second one. We don't see a base there, but we know the base is 10. This is saying log base 10 of 100 equals 2. Well, that's true because 10 squared, or 10 to the second power, equals 100. So this thing here is the exponential form of this log form equation on the left. Okay? Let's do one more. This last one. Well, this is saying log base 2 of 8 equals 3. That's true because 2 to the third equals 8. So there it is. There's the exponential form of this log equation. So one more fun little fact. We often come across an expression that looks like this. The log of 10 to some power. I'm calling it triangle. Okay? So my claim is it's very handy to know how this reduces. And it will be in your mathematical future. If you think about the question this is asking, you'll be fine. So remember, there's a little base 10 here, and then take a minute here and just figure out what you think the answer to that would be. Think about the question we've been asking, and you'll be fine. Let's write that down. This thing really means, what power do we put on 10 to get 10 to the triangle? Once you write that question down, you realize it's probably one of the silliest questions you've ever asked yourself. Right? So with very little work at all, you realize that the answer has to be triangle. Turns out that's a pretty handy fact to know. All right, now we're finally ready. What we're going to do is we're going to take that first rule of logs, and we're going to prove it. So let's go. Let's go try and prove one of these things. Here's the first rule. Log of a times b is the log of A plus the log of B. Okay? So this proof is not going to be one of those statement reason proofs that you learn about geometry. It's just going to be a set of mathematical statements which are true, and then we'll eventually realize, oh, wow, we got what we wanted. Okay. We're going to start off by writing something that may surprise you. I'm going to say let A, the number A, be a power of 10, 10 to the m power, and B equal 10 to the n power. Now, some of you may object to this right away. You might say, hey, how do you know that the number A is a power of 10? How do you know that it's 10 or 100 or 1,000 or something like that? Or 1/10 even, right? Or 1/100th. And how do you know about B being that kind of thing? And my claim is actually, when I write this statement that A equals 10 to the m power and B equals 10 to the n, I'm not really saying that A and B are one of those numbers. So let me show you what I mean here. Okay. Let's imagine for a second we were graphing. I was going to say y equals 10 to the x. You could think of this as A equals 10 to the m. We actually know what that graph looks like. We just did a whole bunch of work with exponential functions. Here's the m axis. Here's the a axis. And our graph looks like this, just like any exponential function. Okay. Well, if you plug in m equals 1, then you know you have to get back a equals 10. If you plug in m equals 0, then you know you have to get back 1. I don't have enough room for it, but somewhere over here I could plug in 2, and it would be way over. So if I plugged in m equals 2, it would go way up here somewhere, and then way up here there'd be 100. But I never said that m has to be an integer. I didn't say m has to be 1 or 2 or 3 or 0. Maybe m's a decimal. So I certainly am allowed to plug in something like m equals 1/2. And if I did that, I'd trace it up, and I'd come across, and what I have here is the square root of 10 as a y value, which is a little bigger than 3, right? And I think if you give it a little thought, you'll realize, hey, wait a minute, what if I wanted to get 23 back as an answer? Well, I could do that. I could just trace across to this graph and trace down. Actually, that's not quite, it would end up out here somewhere. It would be a little bigger than, oh no, it would be fine. It would be something like that. So somewhere in here, there's an m value. I don't know what it is, but if I put that m value on 10, I would get back 23. Okay? That number has a name. That's actually the log of 23. It's the power I put on 10 to get 23. And if you go type in your calculator, you can get that decimal. So what this graph is showing me is that I can basically get any positive value of A back at all, because if you look at the blue graph, and we trace over it in black now, it's completely above the x-axis. So for any value of A we pick, we could trace back to a point on the m-axis. That would work. So that sort of shows us that this statement is okay to make. I can say, hey, A is 10 to some power. Now, there's one restriction. I need to say this, that A and B are both greater than 0. There's going to be no zeros for A and B and no negative numbers for A and B. So let me just say this. You might believe now that A could be some power of 10 and B could be some power of 10. You might not know why I'm doing this. Okay? So this would be a time where things got a little bit dark for us in terms of where we're headed with this problem. Okay. Now, what else can we do? Well, we know we can write any of these things we want in log form. So let's take a minute. Can we write these two things in log form? Okay, good. So this is really saying that the log of A equals m. And if you want, you can put a little base 10 down there if you'd like. But you don't have to, because we just know that it's base 10, right? And in the same fashion, the log of B is n. Okay, so right now I've started this proof in a very strange way. You're not quite sure why I did this, but I promise in a few minutes you'll be fine. So what we're going to do is we're going to take this expression here, and we're going to try and get to that expression. That's my goal. My goal is going to be to try and get the log of A times B. I'm going to start with just A times B for now. So if I do A times B, according to these this new statements I wrote in blue, A equals 10 to the m, and B equals 10 to the n. So I'm going to write that. 10 to the m times 10 to the n. And I claim you know a new way to write that, right? Because when we have the same base and we're multiplying, we could add the exponents. So we can really write 10 to the m plus n power. So we get A times B equals 10 to the m plus n. All right. So right now you might be thinking, hey, this doesn't look anything like what we want to prove, right? We're trying to prove this statement up top, this statement written in black. Well, if I look on the left side, I see the log of A times B. And if I look down at what I have so far, I only have A times B. I really want a log to be there. So I'm going to do that next. I'm going to say the log of A times B is equal to the log of 10 to the m plus n power. Okay. And then I would like you to look carefully at the right side of this equation. If you do that, you'll say, oh, wait a minute. That's a really silly question. So we know this thing on the right here has to be m plus n, because after all, this is asking us, what power do we put on 10 to get 10 to the m plus n? And the answer to that is just m plus n. On the left side, we still have the log of A times B. But then if we go back and just look carefully on our papers, oh, what do you know? Look at this. M equals log A. And N equals log B. And things should be a little clearer, or a little brighter now. This would be replaced with log A. And this would be replaced with log B. And we have proven what we wanted to show. We've got another rule to prove, and I think you could probably do this one on your own pretty quickly. I'm just going to start you off. Here's the rule you want. You want to show that. And I'm even going to start the proof the same way. I'm going to say, all right, so we want to prove this. I'm going to start by saying let A equal 10 to the m power and B equal 10 to the n. And the first thing you should do is figure out the log form of both of these, which you already know. Okay, so that's the log of A equals m, and the log of B equals n. Okay, and then down here, start with A divided by B. All right, so this should happen pretty quickly. Okay. So we know that this is 10 to the m, and this is 10 to the n. And we also learned that when you divide things that have the same bases, we can subtract the exponents. So we get 10 to the m minus n. Okay. So you might be thinking, all right, well, what do I do next? Remember what your goal is. Your goal is to get this expression, the log of A divided by B. So I'm going to take the log of the left side of the equation, the log of A over B equals, and then for the right side of the equation, I get the log of 10 to the m minus n. And there's that really silly question again, right? It's saying, what power do I put on 10 to get 10 to the m minus n power? Well, that's just m minus n. And then we get to finish because we know that m equals the log of A and n equals the log of B. Okay. All right, so far so good. There's one more rule I want to show you, and it actually come up pretty quickly. My claim is if you believe the first rule, that the log of A times B is the log of A plus the log of B. If you believe that, then you probably should believe this. At least for the case when C is an integer. That's what we'll say for just the time being. So I'm going to outline an idea to sort of justify why this rule, rule number 3, should be true. But there's probably a better proof somewhere you can go read another time. Okay, I'll point you in that direction. So I'm going to call this proof lightly. Okay? Let's start with the following. I'm going to say log of a times a. Okay? And you might think, all right, what made me think to do that? Well, I want to make use of this rule somehow. And this rule only works when I have something times something else. It's just that instead of having log of a times b, I replace the b with a. So it's the log of a times a. And according to that rule, this would equal the log of a plus the log of a. All right. Well, that seems pretty straightforward. Well, if you just take a minute now, you'll notice what we've just done. There's a more compact way to write this thing here. Instead of writing a log of a times a, you can write this the log of a squared. And there's a more compact way to write this. If you have the same thing being added to itself, you can just write 2 times that thing. So here we are. Now, if you look carefully at that, this looks just like rule number 3, except c equals 2. So what we've just done is we've shown this rule would work for the case when c equals 2. We have only proved this for the case where c equals 2. Let's go for some more integers. What about the case when c equals 3? All right, you might be surprised. Watch what I'm going to do. I'm going to start this in a very similar way. I'm going to say, hey, the log of a squared times a. Now, I know that a squared times a would be a cubed. But I also know from rule number 1 that this is really the log of a squared plus the log of a. Alrighty then. Well, what can I do with this? Think about it. In the first case, when we did c equals 2, we just showed that the log of a squared equals 2 log of a. So I can replace this with 2 log a plus log a. Oh, well, that looks promising, because now on the right, what do you have? B log a. But on the left, you have the log of a cubed. Alrighty. So what you can see is, in order for me to prove the case when c equals 3, I needed to know that the case when c equals 2 was true. And I already had that. So now I've done c equals 3. Now, without working too hard or imagining too much, you could just think, oh, well, if c was 4, what would I do? You'd write it as the log of a to the third times a, and you'd do the same thing. You'd say the log of a to the third plus the log of a, and then you use this rule on this term and get 3 log a plus the log of a, and you'd have 4 log of a, and then over here you'd have the log of a to the fourth. So we could just keep going on forever in this pattern, that is, and you'd end up with this true for all integers, right? Now there's one problem. I never showed it for like c equals a half or c equals 3/4. It works for fractions too, or decimal exponents. You should be aware of that. The proof for that require a little bit more work than what we did here. Okay? My goal here was to show you how you could get the third rule from the first.